so awesome. So awesome. Anyway, all right, so we're going to talk about, first and foremost, the hierarchy of interactivity. That is, we're going to talk about how strong the various forces in the standard model are. So first of all, we can talk about, we can sort of organize them by, we can sort of organize them by what particles the forces actually impact. So for example, if I'm talking about neutrinos, and I immediately misspelled neutrino, geez, this is not a good day for me already, neutrino, okay? Neutrinos feel the least of the standard model forces. Neutrinos only feel what, Jack?
Is it the strong force?
Say it again.
Is it the strong force?
Say it again. Say it again.
The strong force?
Say it one more time.
The strong?
Say.
No, I'm not going to do it now.
Man, that is so weak.
Yeah.
Yeah. Neutrinos only feel the weak force. They're electrically neutral, so they don't feel QED, or the quantum electrodynamics, and they don't have any color. They're not blue, they're not quarks, so they don't feel QCD. Okay, then we can consider alternatively what we call the charged leptons. So in case, and I haven't really been giving you this organizational dialect. It's not super, I mean, it's good for categorizing things, but the story of gauge invariance is the most important. But recall that leptons are all of those doublets that contain an electron and electron neutrino, a muon and a muon neutrino, a tauon and a tauon neutrino. Then you have all the quarks which you put into doublets, up, down, strange term, top, bottom. So the neutrinos are half of the leptons, they're the neutral ones, and therefore they only feel the weak interaction. So what interactions do the charged leptons enjoy?
Oh. Really?
Yeah.
I mean, if they're charged, I imagine they have QED.
Yes, and?
Also then the strong force?
Also the what?
Is it also the weak force then?
Yeah, and the weak force. Okay? And then you have quarks. Remember, these, really two sets, but three sets of matter constitute all the matter in the universe. So quarks love to interact. They love to play. They feel QCD, QED, and the weak interactions. Okay, so you can immediately see why playing around with quarks sucks. Because you got to take all three of these interactions into account. Whereas playing around with neutrinos, well, it sucks too, because remember the weak interactions are the most complicated of all three interactions. So there's really no simple way to get away with an easy calculation. But hey, Ross, you're going to tell the students that I'm going to be late?
I'm sorry. I was going to.
That's fine. Don't worry about it. Now, when I say this, so first of all, like you observed, you know, if this has no electrical charge, you would say it doesn't feel QED. And it doesn't have any color, so it doesn't feel QCD, okay? This has no color, so it doesn't feel QCD. However, these are what we would largely call direct interactions. And the reason why the distinction of direct interactions is important is because it is possible for, say, an electron to experience QCD indirectly. Okay, so let me give you an example of an indirect process. So, for example, I might consider an incoming electron neutrino and an outgoing electron neutrino, and an incoming electron neutrino and an outgoing electron neutrino. Okay? Now, I'm picking electron neutrinos because ostensibly you might think the only interaction is the weak. But I'm actually going to demonstrate to you that the electron neutrinos can interact indirectly with both the weak QED and QCD. Watch. First of all, if I consider the lowest order diagram, that's simply going to be this. Where this guy right here is what we'll eventually learn to be the Z0 boson. And this has to be the Z-naught boson because the Z-naught boson, and we'll talk more about this when we do the weak interactions, the Z-naught boson has 0 electrical charge, which is what you need if you're scattering a neutral particle off of another neutral particle. If this carried charge, it would have to transfer charge from one to the other, but the charge of this is not changing. This is going from V to V and V to V, or nu to nu and nu to nu. Okay? However, you now know, you should know, that stories of Feynman diagrams can get more complicated. So for example, we would eventually find that we might have to include this Feynman diagram. And what I want you to notice is that what I'm going to write in here is all perfectly acceptable. Yes, these are going to basically exchange Z-naught bosons, but in the virtual existence of that Z-naught boson, we're going to have the Z-naught boson break up into a quark-antiquark pair. And then while this quark-antiquark pair in propagation, this antiquark is going to emit and absorb a photon, and this quark is going to emit and absorb a gluon. So it's a crazy picture, but just notice all 3 forces are present. All right? QED and QCD not present in the basic tree level diagram, but if you get to more and more complicated diagrams with virtual loops and all that stuff, you can bring in all the interactions. Okay? All right, so what we want to do now is we want to focus on QCD. And we'll do the weak interactions. Yeah, go ahead.
Real quick, why can't it be like a gamma photon in between in the first diagram?
Here?
Yeah. Why does that have to be Z-naught between?
Anybody help him?
Only like the bosons can, or the force and particle. Wait, I mean, the Z-naught.
Neutrinos don't experience the QED force.
Why?
Oh.
The only one they experience is the weak force.
Why don't they experience QED?
The interaction.
Because they don't have electric charge. They're neutral. Okay? So that's why this is the only possible tree level diagram you can do for this interaction. Okay? All right. Okay, so let's do it. It's going to get ugly. Well, actually, here's the amazing part. The way that the calculating the Feynman diagrams works out, it's really interesting because basically everything we did with QED, we can largely extract it from the QCD calculation. So the QCD calculations will go very similar to have many of the same ingredients. They're just going to have an extra ingredient, which is going to play an important role, but it's basically like doing QED with color, in color, instead of in black and white. Okay, so let's do it. QCD, quantum chromodynamics, also known as the strong force. All right, this could get ugly quick, but just bear with me. Okay. All right, first of all, hold on. Are we going to talk about QCD or are we going to talk about quarks? What should we talk about first, QCD or quarks? Well, it's interesting because if you're going to talk about quarks, you should actually back up a bit and talk about quarks and QED. Because I did say quarks experience QED, and we've already covered QED. So you might ask, okay, well, what else, what is new and different when you deal with QED with quarks? Well, the thing is quarks can replace any of E plus or minus, mu plus or minus, or tau plus or minus in any QED diagram that you imagine. one important difference, and that is that unlike the electrons, the muons, and the tauons, which all have either plus or minus the electron charge, quarks have fractional charge. So basically, you replace the coupling with E times the square root of 4 pi over h bar c, where E in the charge of, in the case of quarks, becomes Q, which is either 1/3 E or 2/3 E. Okay, plus or minus. All right. But otherwise, the story plays out exactly the same. Well, sort of, right? Because, you know, you can take two electrons and you can scatter them with a photon. But if I send in a quark, which has charge 1/3, can it scatter off a quark that has charge 2/3 with a photon? Yeah, it can. Okay, this is going to come out with 1/3, 1/3. Okay, but then you can do this, right? You can have a particle come in with electron charge E, particle come out, photon, electron E, electron E. Can we do that with, actually we can do, yeah, you can do everything. You can do everything with these fractional charged quarks. So it's very, very, just a restamping of the rules of QED, okay? And for calculations dealing with the electric charge of quarks, the color just comes along for the ride. You don't even have to think about color when you're doing QED with quarks, okay? But now we want to turn our attention to QCD in quarks. Okay? And for quarks in QCD, color is obviously going to play an important role. So let me start by reminding you of the Lagrangian that we eventually got to. So sum I equals 1 to 6, h bar c psi I bar gamma mu capital D mu psi I. What is this I summing over? Can anyone tell me? Otherwise I'll draw your name. Yeah, 6 types of quarks. There's 6 quarks in the standard model, so we're going to sum over all 6. Nice. Plus 1 over 16 pi, d mu a mu minus d mu a. Uh-oh, why do we have an index A on that vector field A? Can anybody tell me, is I right?
It's color space.
And how many, I can't write and answer or ask a question at the same time. How many values does A take? How many? 8. There are 8 generators of SU3, and for each generator of the group you're localizing, you get a gauge field, okay? And then we got this set of nasty terms. Minus g over 16 pi, f ADE, AD mu, AE mu, D, I'll just write one of them and then I'll say there's, oops, I'll say there's 2 more like this. Okay, I won't write these, but there's 2 more terms that are a lot like that one, okay? And now remember that our derivative, our covariant derivative is defined as d mu psi I plus ig lambda dot a mu psi I. Okay, we didn't have to do this in the case of QED because there was only 1 generator, but now we have 8, so we can put a parameter with each generator, a lambda with each generator, okay? So we have to use this sort of dot product in our covariant derivative definition, okay? And also remember that the quark fields, psi i's, come in 3 components. And those components are? Yes, red, green, and blue. Psi red, psi green, psi blue. So what I want you to notice is this is an index nightmare, because we have I, which tells us which quark we're dealing with. Is it an up, down, strange, strong, top, bottom? Okay. We've got A, which is telling us which generator we're talking about. And then we've got RGB, which labels the three components, the three color components of the quark. So it's a bit of a headache, okay? Now, once again, and I'll stress what I said before when I talked about QCD, the color in this story is largely playing the role of charge in QED, okay? But there is a distinction. You might think that red, green, and blue are just different values of the color charge, but that is not what we mean. That's kind of like saying, I got particles with charge +1, 0, and -1. That's not what we mean. These are three different kinds of charge. Okay, so red is not a value of the blue, they're just three completely distinct charges. Okay, they're not different values, because you can have different values. You can have red and anti-red. That's the negative of red. You have green and anti-green. But red and green are different charges, okay? All right. Now, this story seems kind of simple, but there is actually one interesting observation from the strong interactions and the behavior of quarks, which kind of complicates things, and it's something that we'll investigate. That is, quarks do not exist alone. Quarks are not loners. In fact, it's impossible to see a quark by itself. It's impossible. And we'll talk a little bit about why later on, or maybe next time, okay? Rather, they form what are often called hadrons. So a hadron is just this collection of quarks, kind of like an atom is a collection of an electron and a proton, or many electrons and protons, okay? However, hadrons only come in two varieties, so we can just go ahead and scope them out. There is mesons, which are in the form of a Q bar, that is a quark and an antiquark, okay? And then they also come in the form of baryons. Baryons are combinations of either 3 quarks or 3 antiquarks. Okay? So we're going to talk a little bit about why this might be that you only see the quarks in these bound states of mesons and baryons, and we'll do a calculation or two to support that. But it's actually it's actually a conclusion that has not yet been proven. So if you can prove it, you can go get your Nobel Prize, all right? We'll look more on that later though. Okay, so now there is a useful way to think about quark interactions, and that is the following. So imagine I have a vertex in my diagram, so I'm gonna have a quark come in and a quark go out, and I want the color of the quark to change. That obviously can happen, so I can have red turns into blue, okay? Of course, it's gonna do this by having an interaction mediated by a gluon, okay? Just so you're aware, with electromagnetism diagrams, we drew wavy lines for the photons. For gluons, we draw spirals. And then for the weak bosons, I'll point this out later on, for weak bosons, which I've already done this, you draw jagged lines. Okay? There's a certain sense in which you don't even have to label that as a photon, you just draw the wavy line. You don't have to label this as a gluon. That just shortens it. But you gotta distinguish between photons, weak bosons, and gluons, okay? Now here we go. So I have red coming in and blue going out. So if I want to think of this as a gluon going in, then what would the color assignment of that gluon be? It's Say it again?
Anti-red, blue.
Yeah, it would be anti-red and blue, because it's bringing in anti-red, which cancels this red, and left over is blue going out. Or I could imagine this as a gluon going the other way, in which case the color combination would be red, anti-blue. Okay? Does this make sense? All right. Now, you might think from this picture that, oh, you know, gluons, they're going to be really easy to sort out because you basically just put in a color and an anti-color for gluons, right? I mean, does that make sense? If I'm going to have a quark come in and go out and it's just going to change color, I'm just going to have, you know, a color and an anti-color. It could be different combinations of colors and anti-colors. Okay, but that's basically how I'm going to write the gluons, right? No, it's never that easy. Turns out if you want to specify the states of gluons, you should actually rely on what is called an octet of states. These are a set of eigenstates, or these are states that the SE3 transformation generators carry us between, and they're going to take the following form. And this is going to take me a minute, but I have to write these down because we're going to use these. So first there's state 1, which is R B bar plus B R bar. There is state 2, time to tell a joke. Nobody brought your damn jokes. Half of you have computers open. Why aren't you looking up jokes? Physics jokes, at least. Jeez, terrible. I gotta draw 8 of these. All right.
Man walks up to a horse and asks, "Have you been reading the thesaurus again?" The horse says, "Nope."
Wait, say that again. I think I missed the first part.
A man walks up to a horse and says, "Have you been reading the thesaurus again?" The horse says, "Nope."
I don't get it. Sorry.
The horse talks.
No, because the horse is supposed to say nay, but no is a synonym for nay.
Oh.
He has not been.
So it should be the horse says nay.
Well, the horse is lying. He's a dirty
Oh, wait,
liar.
that wasn't even intentional, dude.
Well, I mean, why can't the horse just be truthful and say nay?
Have you met a horse? They are mischievous, evil creatures.
I mean, that just sounds like you're biased against horses, I don't understand that.
Okay, minus I over root 2. I'm just gonna resume my talk and just read off what I'm writing. Okay,
You asked for jokes.
yeah, I know. Okay, I've got the 8th state, and I'm gonna go ahead and call him Davis. Can you guess what the 8th state is? No, Ross, you can't help him. Anybody want to help him?
1 over root 2, B anti-B minus G anti-G.
No. Any other takers? Yeah. One is not a state. Do you have a guess?
I mean, is it, I guess, 1 over root 2 RGB plus R bar B?
That's really close. That's really close. You'll be proud. That was so close. 1 over root 6.
Oh,
R bar plus B bar minus 2G bar. That's obvious. Come on, people. No, this is not obvious at all, okay? All right. Now, one thing I want you to notice about this is that states, well, actually, I'll let you tell me, and I'll let, Tanner. Tanner? Henry, which of these 8 states are colorless? I'll give you hints, there's 2 of them.
8.
And? 3, exactly. Does everybody see that? 3 has red, anti-red, blue, anti-blue, and then 8 has each of them. The rest of them are mixed, okay? Now, once again, all of these are transformed into each other by SU3 transformations. There is left over what is called the singlet, which is a state which is invariant under the SU3 transformations. And we might call this state 9. Does anyone want to guess what state 9 is? Cameron. There you are. I knew you were here. I couldn't find you. Cameron, which state do you think is invariant?
I don't know.
No, it's going to be something like a combination of these, but it's a very particular one. Think about it for a moment. Ross, you should just put your hand in the sling. What do you think an invariant combination of quarks and antiquarks might look like? Would it need to have all of them in there? Yes, because you could have a gluon take a red and turn into a green. Okay. Do you think they should be there in equal portions? Yes. Yes. Okay. Just so that we don't waste too much time guessing. 1/√3, red bar plus blue bar plus green bar. Okay. Now, why am I talking about octets and singlets? Well, here we go, folks. All quarks, this is the matter, which I said has to exist as mesons or baryons. All quarks that are mesons must live in this state. We'll see why in a bit. Okay? That is, this is a colorless state. And it's invariant under the SU3 transformations. Okay? Whereas the gluons must be in these states, which actually you should suspect because remember we have 8 gluons. I just gave you 8 states. All right? Okay. If, and this is just a big if a 9th gluon existed, if there was a gluon that was in addition to these, it would live in this state. But that gluon would be color neutral. So that gluon would play the role of a photon in QED. In fact, with the 9th gluon, we have QCD, which is SU3, it would just go to U3. Okay? But at any rate, all right, so now I'm going to put some comparative notation on the board, which I think to start with will help you with where this is going. And then we'll get into the Feynman rules. So let's compare the 3 theories that we've already done, or that we've already done, the 2 theories we've already done with what we're doing. Sorry. So we're going to do ABC, QED, and then QCD. Okay? So we're going to start with external state labels. Okay? And what did we use to label external states, Connor, in the ABC theory?
To label external states, we used P.
Yeah, exactly. Nothing. Remember? There are no properties of the external states except how fast they're moving. They don't have any degrees of, they're not anything in that theory. They're scalars. There's nothing that you have to specify. So we didn't specify anything about the external states of ABC. Whereas in QED, we have to specify their spin states. So we would call them either UU bar or VV bar. And then For the photons mediating the interactions, we would also have to specify their polarizations. Okay? So of course this is matter, and this is photons. Okay? Well, for the case of QCD, once again, we're going to have to specify the spin of the incoming and outgoing quarks, okay? But it turns out that each quark has not only spin as a degree of freedom, but also, well, this is QCD, so we're not worried about the electric charge. It has, huh?
The color.
Color, they have color, okay? So for incoming and outgoing quarks, we will be specifying their spin and color as just another factor. And then U bar C dagger, V C and V bar C dagger. And of course this is the matter part of the story. And then we have gluons. Well, gluons are once again going to have a polarization because they're again these vector particles, the A mu's are the gluons. But we're going to have to give them a little bit more information, okay? So in this case, we're going to give them something we call A alpha. And then we can have epsilon mu star A alpha star. All right. Now we're going to look at internal propagators. Okay, that is if I have a diagram, the external states are these things, and then the internal propagators are what we have to put in for things like this. Okay, and then we'll end with the vertex factors, and you know that's the whole story. You do your external states, your propagators, and then your vertex factors, and that's it. Okay, so the internal propagators in the ABC theory took the form of I over Q squared minus M squared C squared. For an internal matter particle in QED, we had I Q slash plus MC over Q squared minus M squared C squared. And then for the photons, we had minus I eta mu nu over Q squared. Okay? For the internal propagators in QCD, it's actually the same story. All right? However, for the propagation of gluons, it's going to be a bit more complicated. We're going to have a delta function in there. And then last but not least, there are the vertex factors. All right, so in the ABC theory, we had A, B, C, and the factor we would put in our expression for M was just minus IG. Okay? In QED, we have only this diagram. And in that, and whenever that vertex occurs, we'll write I, G, E, gamma mu. Okay? The G's are playing the same role in all of these. And then for QCD, recall that it's a bit worse because we have the quark gluon terms, which are going to have vertex factors of the form minus I, GS over 2, lambda alpha, gamma mu. But because this is a non-abelian group, in addition to the QED version of the story, we also get these lovely interactions of gauge fields with other gauge fields. This is AAA, that's an interaction. So we get new vertices. In fact, we get vertices like so. Yeah, and then we also get a four vertex. Okay? I'm not even going to write down what those vertex factors are. They're really long. So they're in the notes, so you can look at them. Okay? So clearly, QCD has got a lot more you have to deal with than the ABC theory for sure, but even QED. All right? But what's interesting is what is in the QED theory is in the QCD theory. Notice I've still got U's and U bars and V's and V bars and epsilon Mu's. And in fact, I've got the same propagator here, it's just I got this delta alpha beta. Now, these vertices are not in QED, so this is a new ingredient, all right? But we're not gonna worry about that right now. Okay, so the question one might be asking is, all right, what is C A alpha, lambda alpha, and, well, I should just quickly say, these are specified in terms of F, GS minus GS, F alpha, beta, gamma, and then a whole bunch of crap, okay? All right. So what is C A alpha, lambda alpha, and F alpha, beta, gamma? All right. So let me erase this and get to it. Okay. First of all, what is C? C is the three colors in charge space. So charge space is three-dimensional. You've got three different charges, not three different values of a charge, but three different charges that you can assign to a quark, okay? So we might as well just give them a basis in this three-dimensional space. So we'll call C1 1, 0, 0, and that's just our mathematical notation for red, okay? And then similarly, C2 0, 1, 0, that will be blue. And then C3 0, 0, 1, that will be green. Okay? Now, we can always take C, which is the composite color state of a quark, because remember it can be mixed from red, blue, and green. It doesn't have to just be red or just be blue or just be green. We can take this to be a linear combination of these three colors, but these coefficients can be complex. Okay? That's a given. You're always allowed complex stuff in quantum field theory. Okay? But this means, of course, that if I dagger a C, this is going to be C transpose complex conjugate. Okay? So even though these are real, the vectors that we can make with this as a basis are complex because the coefficients can be complex. Okay? This will just be an important detail for later on. All right, so now the A alphas. There are 8 gluons. So we can label these A alphas as A1, 1, 0, 0, 0, dot, dot, dot. A2 is 0, 1, 0, dot, 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 etc. Okay? And this is a basis in the 8-dimensional Hilbert space of gluon states. All right? So basically, this is going to indicate this. This is going to indicate this, et cetera, et cetera. All right, we're just setting up a matrix language. These are not really numerical. These are numerical. Okay? So we got to move away from the red-blue color labels to numbers. So we're just using ones. It's just where we put the one to specify whether it's red, blue, or green. Okay, or whether it's in this combination, this combination, this combination. Does everybody make sense? This is this. This is this. This is red. This is blue. Okay, I'm just making numerical identifications so that we can put them into equations and multiply them out and get numbers versus letters. Okay? All right. so now for the lambda alphas. Now recall, in QED, and I'm just gonna write this over here, in QED, gamma mu AB linked spin space to space-time. Okay? Now, I wrote gamma mu AB, but what are the AB indices? Do I usually put them on there? No, but what are they? They're spin indices. Okay, unfortunately, we're working in 3+1 dimensions, and so it turns out the space-time index takes 4 values. So does the spin index, but they do not correspond to the same thing. This corresponds to time in the next, then y, and then z. This corresponds to the first, second, third, and fourth component of spin, which has nothing to do with time, x, y, and z. Okay? All right? But what's important is this is a single object which connects space-time to spin space. Okay? That's this connection. All right? In this case, as you might guess, this secretly carries some extra indices. All right? But these indices are telling us that this provides a connection or a linkage between the three-dimensional Hilbert space of color to the H8 of gluon space. Okay? That is, this corresponds to 8 3x3 matrices. Okay, so the ij take values 1 to 3. So in terms of the matrix indices, these are 3x3, and then there are 8 values of alpha, so there are 8 of them. So again, this is linking two spaces, but it's not linking space and space-time. Rather, it's linking color space, which is indexed by I and j, and it's a matrix in color space, to the 8-dimensional gluon space. Okay? All right. Now, just like we did with the gamma matrices, where we left off these spinor indices, we're going to leave off these color indices on lambda. Okay? And we'll also leave off the color indices on the C's. Okay? And then last but not least, there is F alpha beta gamma, or I guess eta. Okay? Shadely. Any idea what the F alpha beta etas are? These things right here? Okay. So what's the difference between the group underlying strong interactions and the group that's underlying QED? What are those two groups? Groups of transformations. So for QED, the underlying group is U1. For QCD, what is it? SU3, okay? There's a big difference between these two groups. This one has a property which this one definitely does not have. What is it? Any takers? This is a billion, this is not. That means if you take the commutator for an abelian group, it's always 0. If you take the commutator for a non-abelian group, it's always equal to these structure constants. So it's taking the structure constants to 0 that makes a group abelian. That's a more general way to think about it. Moreover, it shows how QCD would reduce to QED, because if we took F to 0, all of these interactions of gluons with gluons would go away, and this theory would look a lot more like QED, because photons don't play with other photons. Okay? They just play with themselves. All right, so these are the structure constants. Of SC3 Lie algebra, or Los Angeles, you pick. Okay? Now, we're about to do a calculation, or 2, or 3, or 4, or 5. But anyway, there is one more complicated thing which we have to be really careful about. And we're not actually going to do it, but I just want to show you how you might approach it. If you have a diagram with an internal loop, okay, then it turns out that there are variations of these diagrams which are very similar, but they look just a tiny bit different. Like this might be different quarks or something like that, okay? I don't have a concrete example in mind, so what I'm doing is kind of heuristic. However, this theory has asymmetry, and it turns out if these diagrams are related by the symmetry, then you should not write them individually. You should just write one example and use that for your calculation, okay? So if you did more than one of these, it would be degenerate. So there's an approach to dealing with that degeneracy from the symmetry, and that is to add in extra fields which cancel off any of the terms which are actually degenerate with other terms. So you can either, every time you write a diagram, carefully think about whether these are degenerate with it, or you can add in extra fields to the theory which automatically cancel these degenerate diagrams, and those happen to be called Faddeev-Popov ghosts. But we're not going to go any more with Faddeev-Popov ghosts. Okay? All right. So, now, I promised you that we're going to do calculations and it's going to have revealing results. There are two things that we're going to demonstrate through our calculations. Number one, we're going to illustrate why singlets are the only states allowed for quarks. Remember, gluons take the octet, quarks can only exist in the singlets. We're going to do a calculation that will suggest why this is the case, although it won't prove it, and I'll explain why it doesn't prove it in time, okay? And then we're going to answer another question, which is, the strong force seems to be weaker than the electromagnetic force. So what the hell is in that naming? Why do you call it the strong force if it's weaker than the electromagnetic force? Okay, and we'll see the answer to that through an analysis of Feynman diagrams. Okay, but first and foremost, let's go ahead and get our hands dirty with a calculation. And like I said, what's going to go into this calculation is going to include everything we did with QED. So all of that shit we did with QED, it's just going to have extra stuff due to the color story. So I'm going to erase all this, and we're going to get going on the calculation. All right. So let's consider a meson. Q1, Q2 bar. Okay? And to motivate why this meson must be in this state versus this state, what we can do is we can say, okay, I'm going to consider the two quarks, and it's those two quarks that are in this meson, and I'm just going to pretend they're asymptotic, and they're going to come in, they're going to interact, they're going to go out. And what I want to figure out is their interaction attractive or repulsive? If they must be bound together, would the interaction between those two quarks be attractive or repulsive? Attractive. If it was repulsive, you'd be like, why the hell are you together? Break up already. Okay? All right? So here is the argument I'm going to make. I'm going to take these two quarks and I'm going to put them in one of these states, and then I'm going to put them in this state. When I put them in one of these states, we'll find, and it's true for all of these, that the interaction is repulsive. But if I put them in this state, it's going to turn out that the interaction is attractive. Now we know that they cannot escape. We know they're stuck together, and again, I'll talk more about that later. So the fact that any of these states gives me a repulsive interaction, whereas this is the only one that gives me an attractive interaction, tells me that they must exist in this state and not in these. Another way to say that is that that pair of quarks must be colorless, because this is the only colorless version. Okay? So here we go. Let's go through a calculation. Let us consider.
Weren't 3 and 8 also colorless?
Well, they are, but they're not invariant, so they're not going to play that role in the story. All right, so we've got anti-down coming in and out, and we've got an up coming in and out, and we're of course going to have a gluon exchange between them, which I'm going to give a momentum Q. I'm going to call this 1, I'm going to call this 3, call this 4, call this 2, which of course you can take to be labels for the momentum of those external states. And then the interaction that we're dealing with, just for concreteness, is going to be an up plus an anti-down quark being scattered into an up plus an anti-down quark. Okay, we're not changing the content. Nothing is getting created or destroyed. All right? So if I calculate M using the Feynman rules for QCD, which I've written down all the ingredients and now I've erased them all, but they were on the board a little while ago. Okay? Remember I had this table here and I had the external states, the propagators, and then the vertex factors. We just used that same prescription that we did for QED, following all those different rules, but using those factors, and we'll construct a value for M, and it will turn out to look like this. I, U bar 3, because remember if we want to, so you can either follow you can start with an outgoing particle or you can start with an incoming antiparticle, okay? So I, U bar 3, and then this gets its color factor, so I'm going to give that a label 3, just so we know it's the color of state 3, and that's going to be daggered. And then we're going to have minus I GS over 2 lambda alpha gamma mu. That's a vertex factor. And then we're going to have U1 C1. So basically started here, came in, hit this vertex, and then came out here. So that's the factor for this. This is the vertex factor, and this is the factor for this. And then we're going to have, where am I? Yeah, so we're going to have our propagator, which I'll just throw in the middle here, minus I eta mu nu delta alpha beta over Q squared. And then we'll have, following this line in and that line out, we'll have V bar 2, C2 dagger, whoops, dagger over C2. And again, minus I G over 2 lambda beta gamma nu V4 C4. Okay? Well, of course, everything in here is complicated. You've got spinners, you've got spin matrices, you've got color matrices. It's a really screwed up story. But notice something. There are two complicating spaces in which this thing is expressed. There's spin space and there's color space. And the good news is that color space and spin space commute. They have nothing to do with each other. So I can, for example, take lambda alpha, which is trivial in spin space, and I can move it anywhere I want with regards to the spinners and the spin matrices. So too can I do it with these color vectors. So there's nothing that keeps me from taking spinner, spin matrix, spinner, and just pulling those tightly together, pulling all the constants out front, and then doing color, color matrix, color together. Does that make sense? Okay? So at the end of the day, this is going to give me, after the delta 4 or 2 pi 4, delta 4 p in, p out, and times I. That's the standard prescription for what you do to get the expression for m. This is going to give me minus gs squared. And I should have put, yeah, I should have put, not G2, sorry, it's GS. I don't know what the hell is the problem today. GS, sorry, okay. Minus GS squared eta mu nu over Q squared. And then here we go, we get it cleaned up. U bar 3, gamma mu, U1, V bar 2, gamma V, V4. Okay. Times this thing, which is going to be C3 dagger lambda alpha C1 quantity times C2 dagger lambda alpha C4 times 1/4. Okay? Now here is the important observation. Are you ready? This term right there is exactly the same as in QED if we let GS go to GE. That is, if we let the strong coupling go to the electric coupling. This is exactly what we would have gotten in QED. Okay? But of course, this is if we're dealing with a positively charged particle scattering with a negatively charged particle. All right? Now, are you ready? This is screamingly simple. Is this interaction attractive or repulsive? It's attractive, okay? So what we can now focus on to determine whether this interaction is attractive or repulsive is basically the sign of this. This is what we call the color factor. It only involves color things, color matrices and color vectors. If this thing comes out to be positive, then the interaction is attractive. If it comes out to be negative, then the interaction is repulsive. So all we have to do to prove that in this case it's attractive and in this case it's repulsive is calculate these color factors using all of this information. Okay? So here we go. In order to calculate the color factors, I'll keep those up there. So first of all, we've got these things. We're going to need the lambda matrices, okay? So let me write down our matrices. Remember, there are 8 lambdas and there are 3 by 3 matrices. Let me write them down very quickly so that I tell the joke. That's hilarious. geometry, what am I doing? I don't know why I'm raising some of mine. Now there's 5.
Is a second horse joke acceptable?
Yes, definitely.
So, a horse walks into a bar, sits down, bartender asks him, "What are you thinking?" The horse answers, "Nothing," and disappears. See, this is a play on Descartes' statement, "I think, therefore I am." I would have explained that first, but if I had, I would be putting Descartes before the horse.
Good joke. Can you guess what that one is? What's missing?
So, no.
No?
No, I can't guess it. I mean, I could say a bunch of numbers, but I don't think that would be helpful.
I thought it was pretty obvious. Okay?
Good, you should guess these.
Yeah. Okay, so now, in order to do this calculation, we're gonna need our C's and then we'll put in a lambda. So let me show you how this works. First of all, let me see. Why did I do that? Oh, yeah. So, okay, yeah. So here's what I wanna do. First of all, these are the D and the U is the type of particle I'm dealing with. But now I need, in order to assign these color vectors, I need to assign the color combination of these. So what we're gonna do first and foremost is we're gonna say, okay, let's say that I have a anti-blue antiparticle. Obviously, this is the antiparticle that's going backwards in time. That's how you know antiparticles from particles. And then we're gonna have red for the particle, okay? Now remember, this is 1, 2, 3, 4. So, geez, Jet, what is C1? What is the color factor for this thing?
Is it just 1, 0, 0?
Exactly, it's the red vector. Okay, so we've got 1, 0, 0. What about for 2?
That'd be 0, 1, 0.
0, 1, 0. 3?
1, 0, 0 again. And then 0, 1, 0 is the last one.
And then 0, 1, 0. It's that easy. Okay? Now all we have to do is construct this thing. Now notice alpha is repeated. It's repeated because this had an alpha index, this had a beta index, but we had delta alpha beta. So that sets them to be the same. So we need to sum over these alphas, and there are 8 of them. So we're literally going to say, okay, let's do C3 dagger, that's this. This happens to be real, so we could just transpose it, we don't have to complex conjugate it. So this is going to involve 1, 0, 0, and then lambda 1, which is up there, I'm just gonna write lambda 1, times C1, which is this, 1, 0, 0. And then this is going to have C2, which is this, transposed, times lambda 1, times C4, which is this. Okay? Plus the same thing with lambda 2, plus the same thing with lambda 3, etc. All the way through lambda 8. Yes?
How do we know that the anti-blue is 0, 1, 0, not
Because the fact that it's an antiparticle is already encoded in the spinner that you're using, so you assign it the same color, and because it's an antiparticle, it gets the antiparticle version of the color charge. So it's the same space in, it's the same state in color space, but it's an antiparticle version of it, so it's the negative value of the charge. So this is just specifying that it's blue or green or red, not that it's anti-blue, anti-red, or anti-green. You don't need that for color space. Does that make sense? You're encoding the fact that it would be a negative green or negative blue or negative red or whatever through the fact that it's an antiparticle, and that's described in terms of its anti-spinner. If you tried to do an anti-color and an anti-spinner, the net would be a positive color, so you don't want to do that. You want the negative to come in there, and one part of the story, and it's going to come in the fact that it's an anti-spinner. Okay? Yes?
Does the fact that the quarks are up and down have anything to do with their colors? Where does that come in?
No. Quarks, no matter what kind of quark, so the up, down, strange term, top, bottom, those are the different kinds of quark particles. Each and every one of those can be red, blue, or green, or combinations of red, blue, and green.
So what differentiates up and down?
Nothing in this case. Nothing. What I'm talking about has nothing to do with the types of quarks. It's only got to do with their color. I'm saying the colors have to be in this singlet configuration. I'm not talking about the quarks themselves. Everybody follow that? It's like if I made an argument about, I can take a charged particle and a negatively charged particle and they can form a bound state. I didn't say if I was dealing with an E and a mu or an E and an E minus or an E and a tau. That doesn't matter, it's just the charge that determines whether they can be in a bound state, that's it. Similarly here, the color is the only part of this story I care about. I'm just, calling these up and down so there's not more diagrams to contribute. Does that make sense? Okay. All right, so now, I'm not going to write it up here, I'm just going to give you the answer, but hopefully you see how you do this. Like literally, this is a 3x3 matrix. So you hit it with this, or you multiply this by it, and you multiply, this gives you a number. This gives you a number. What do you do with those two numbers? You multiply them together. And then what do you do with these two numbers? Multiply them together and add them to this, and dot, 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 dot. So you get 8 terms, okay? Everybody follow? So at the end of the day, F is going to be 1/4, 0 plus 0 minus 1 plus 0 plus 0 plus 0 plus 0 plus 1/3, which is minus 1/6. Okay, most of them give you 0, which is obvious. These two things are in a sense only picking out one component of the matrix, and most of the components of the matrices are 0. All right? So there you go. The color factor is negative. Oh, actually, sorry. I meant to say, this is me being stupid. This is red and blue bar. That's this guy right here. All right. So actually, is this guy right here? No. This would be a combination of red and blue bar there, and then blue and red bar there. We'll do a combination in just a moment because we're going to have to do it with this. But I guarantee you, if this comes out this way, then this combination comes out that way as well. Okay? But my point, though, is that you could put any of these states in for the color assignments, any of these octet, not the singlet, but any of the octet, and the color factor will always come out to be negative. Okay? But that's basically controlling the sign of this result, which is attractive. So if you negate it, it's going to be repulsive. And there's an argument for the sign of this thing being responsible for whether it's attractive or repulsive in the notes, but we're not going to go through it. Okay? Does everybody follow? What happens now is we put it in this state. And if we put it in this state, we should find a positive number. And let me just give you a hint as to what that looks like, and then we'll go ahead and break. So in order to put it in the next state, what we can do is we can say, okay, fine. I'm gonna take the 2, the 4, Gluon, 1, and 3. And to put it in this state, how are we going to put it in that state? I mean, here I just said this is red, this is blue, this is red, this is blue. And then I put those factors in, but I want it to be in red anti-red plus blue anti-blue plus green anti-green. How am I going to do that? Well, let's just write it down. So I'm going to assign C1, C2, this is the incoming states, to be in 1 over root 3, 1, 0, 0, 1, 0, 0, plus 0, 1, 0, 0, 1, 0, plus 0, 0, 1, 0, 0, 1. Okay? That's just red anti-red plus blue anti-blue plus green anti-green. Okay? And this is the state of the incoming particles. The state of the outgoing particles must be the same, so we can write down the exact same thing for C3, C4. Okay? Now what is F going to look like? Well, F in this case is going to look like the following, and this is the color factor. The color factor is going to end up being 1/4, here we go, and I'm just going to write down that factor, C3 dagger, lambda alpha, C1, C2 dagger, lambda alpha, C4. Okay, I'm just putting these numbers as subscripts a little bit quicker. I can write this as 1/4, 1 over root 3, C3 dagger, lambda alpha, and now I'm going to take C1, C2, which is this factor right here, and I'm going to replace it with this, okay? So once again, it's 1, 0, 0, 1, 0, 0, plus 0, 1, 0, 0, 1, 0, plus 0, 0, 1, 0, 0, 1, okay? Times lambda alpha C4. Everybody follow? Now I can take C3 and C4 and I can replace them by this same combination. So at the end of the day, and I'll just write this down and you can stare at it for a moment, it'll be obvious, I'm going to get 1 over 4, 1 over root 3, another 1 over root 3 from writing C3 and C4 in the same fashion, and then I'm going to get the following. I'm going to get 1, 0, 0, lambda alpha, 1, 0, 0, 1, 0, 0, lambda alpha, 1, 0, 0, plus 0, 1, 0, lambda, plus 0, 1, 0, lambda alpha, 1, 0, 0, 1, 0, 0, lambda alpha, 0, 1, 0, plus, et cetera, et cetera. Okay? Hang on a second. I actually think I should have written these as row vectors, so forgive me for that. So the second vector in each of these should be a row vector, but don't worry about it. Oh, no, actually, sorry, no, it's fine. No, yeah, so these should be transposed. Because this is CC and this is CC dagger, so the second one should be transposed, but that's fine. Okay, and that's how I get column row, okay? At any rate, just look at this one term. All I do is I take lambda 1 and lambda 1 and plug them in and evaluate this term. And then I do the same thing with lambda 2 and lambda 2 and evaluate this term. I do this 8 times. Then I do it 8 times here. And then I do it 8 times here. Okay? Simple but tedious as crap. So you just want the answer, right? Well, the answer is, actually you can simplify it because this turns out to be 1/12 lambda alpha ij lambda ji alpha. Now the lambdas are matrices, remember, and now I'm actually expressing the index notation of those matrices because now I want you to realize that in matrix language, what is this operation? What am I doing with the matrices? I'm transposing, but I'm going to get a scalar in this spin space. Close. It turns out that this is just 1/12 the trace of lambda alpha lambda alpha. And the most important result, and you can calculate this because this is just, you know, lambda 1 plus lambda 2 plus lambda 3. You add all those matrices together and you take the trace. This thing is 16. Does the number matter? What matters about it? It's positive. Okay? So, to finish up, we have the observation that quarks must exist in these bound states. So the interaction between them must be attractive. But what we just learned is if I take 2 quarks and put them in a state of this color assignment, it's going to be a repulsive interaction. Only in this color state is it attractive. So this means that the quarks must be in this colorless state. You can also apply the same argument to a 3-quark baryon. It's way the hell harder. But we'll start with that next time. All right? Thank you all for putting up with me.